In this module, you're going to learn how to declare and use variables, and what the difference between primitive and object reference types is. In this module, we'll be discussing variables. We'll learn the syntax for declaring a variable, the naming rules for variables, as well as how to initialize a variable. We'll also learn about the 8 Java primitive data types, how to modify variables using operators, and we'll talk about promotion and typecasting. Variables can be declared in Java in 2 different places. They can be declared in the body of a method, in which case they are local to that method and only exist during the execution of that method, or they may be declared in the class definition itself outside of any method body. In that case, they are called instance variables or attribute variables. In the example we're looking at here, we have 5 attribute variables or instance variables, since they are declared outside of any method body but inside the class shirt. In this case, when dealing with attribute or instance variables, these variables exist or come into being when an object of that class type is created. And each object of that class type will have its own set of these variables. So we see on the right hand side we have 3 shirt objects. Each shirt object has its own shirt ID, price, color code, description, and quantity and stock variables. That is why these variables are called instance variables, since each instance of the class shirt gets its own set of these variables. Now these attribute or instance variable declarations may occur anywhere inside the class definition as long as they are outside of any method body. Typically, we put them first before any method declarations, but they could come after the method declarations, between method declarations, anywhere in the class definition as long as they are not in a method body. Now that we've seen an example of variable declarations, as well as learned a little bit about where variable declarations can go, let's take a look at the syntax in more detail. So go ahead and roll over the modifiers link. The modifiers are optional special keywords that modify the way the variable functions. Some of these optional keywords are public and static. As we go through this course, we'll learn a few of these and see what they do. The first thing, though, that is always required in a variable declaration is its data type. You must always specify the type of information that a variable will hold. Java is known as a strongly typed language. What that means is every variable or piece of data in the program has a data type attached to it. This type can be any of the primitives that we're going to learn about in this chapter, such as int, float, double, or it can be an object reference type, which we'll also be talking about later in this course, such as string, customer, shirt, etc. The next thing that is always required is the identifier. That is the name that you are going to assign to the variable. We'll learn more about the naming rules and naming conventions in just a little bit. Lastly, we have an optional initial value that you can assign to the variable by using the assignment operator. This value must match the type of data that you have specified that the variable will hold. Now it's time for a self-check to see what you've learned. After you've answered each question, click Check Answer to see if you're right, or to see what the correct answer is. Java is an object-oriented language, so most of the time you will be interacting with objects and creating objects. But we do need some simple data types to act as the building blocks for creating our objects. In Java, you have 8 primitive data types. All the other data types that you're going to create are objects. So here we have a table showing us the 8 different Java primitive data types. The first 4 are the integer data types. That means they hold a whole number without any decimal place. And they hold varying ranges of values and take up varying ranges of memory. So we have the byte, short, int, and long. The byte is the smallest. It takes up 1 byte of memory, or 8 bits, and can hold values from -128 to positive 127. The short is the next integer data type. It can hold values from negative 32,768 to positive 32,767 and takes up 2 bytes of memory, or 16 bits. The int data type can hold values from around negative 2 billion to positive 2 billion and takes up 4 bytes of memory, or 32 bits. Now the long data type can hold very large numbers, from about negative 9 quintillion to positive 9 quintillion, give or take a quintillion here or there. And it will take up 8 bytes of memory, or 64 bits. Those are our whole number data types. Then we have 2 floating point value numbers. These are the numbers that can hold decimal places. We have the float and the double. And as you can see, their value ranges are quite large. The float takes up 4 bytes of memory, whereas the double takes up 8 bytes of memory. The next data type is the Boolean. It can only hold 2 values, either false or true. The char data type is a character, one single character, and can hold any of the Unicode characters. Unicode is a character set that holds more characters than the ASCII character set that most of us are used to. So it holds all of the ASCII values that we are used to, the letters, the numbers of the English language, plus many, many international characters as well. And the char data type takes up 2 bytes of memory. Now in Java, even the literal values in your code are assigned a data type. So for instance, looking in the literal column, if in your code you have the number 3, that 3 would be designated as an int. If you put a capital L after the 3, that 3 would be considered a long literal value. If you put 3.0f, then it would be a float. If you put 3.0 without the f, then it would be a double. Then for true and false for the Booleans, the word true, all lowercase, is a special keyword for the true Boolean value, and false is the keyword for the false value. Then if we put a single character in single apostrophes, that would be the char data type. Then, besides these literals, we have some other special ones. Let's go back up to the int row. You notice if we put a 0 in front of an integer, then it's considered to be in octal form. If we put 0x in front of it, it will be hexadecimal form. Also down in the floating column, we can also use exponential notation. So 3.0e to the 2f would be equivalent to 3.0 times 10 raised to the second power as a floating point number. Then we also have 3.0e2 without the f, which would then be a double. Also note that you can use a capital E or a small e. The same thing goes true for the f for floats. You can use a capital F or a small f, as well as for the longs. You can use a capital L or a small l. Also note there is no literal for a byte or a short. Those types of values can only be assigned to variables of the byte type and the short type, and are automatically converted to byte or short at assignment time. Now it's time for a self-check to see what you've learned. After you've answered each question, click Check Answer to see if you're right, or to see what the correct answer is. In the previous slide, we saw the different data types that we can assign to our variables. For instance, byte, short, int, and long. But besides assigning a data type to our variables, we must also name our variables. So here we have the rules and naming conventions for variables. The first 4 bulleted items are the rules. These must be followed or the compiler will give you an error. The last 2 bulleted items are naming conventions, which means that they are generally followed by most Java programmers, but they are not going to be enforced by the compiler. So let's take a look. First, our variable names must start with either an uppercase or lowercase letter, an underscore, or a $sign. These are the only initial characters that you can use for your variables. After you use the initial character, or underscore, or $sign, you may also use numbers in addition to the letters, underscores, and $signs. Next, no other types of characters are allowed in your name. You can't use question marks, hash symbols, greater than symbols, none of it. And no spaces either. It must all be one word. Also, you may not use any of the Java technology keywords, which you see in the chart above. These are reserved by Java and you cannot use them for your own variable names. These are the rules that you must follow when you name your variables. These rules will be checked by the compiler, and if you break any of these rules, you will get an error message. The last 2 bulleted items are the naming conventions I talked about earlier. These are generally followed by most programmers, but again, the compiler will not give you an error message if you do not follow these. First, you should begin each of your variable names with a lowercase letter. We'll see some exceptions to this rule, for instance, when defining constants. Also, if you have a variable name that is the combination of multiple words, then you should use a lowercase letter for the first word and then capitalize each subsequent word in the name. There are several different ways to declare and assign a value to your variable. Let's take a look at those ways here. First, click the declaring and initializing a variable in one line. So here we've declared a variable called price, which is of type double, and we've initialized it to 12.99, all in one line of code. Now click the second link, declaring and initializing several variables in one line. Here you see we have our price variable from before, but we also have a wholesale price variable, which is also of type double, and it will be initialized to the value 6.99. Notice the comma that separates the 2 variables. You may declare and initialize as many variables in one line like this as you wish, but all of the variables will be of the same data type, in this case, double. Click the third link, declaring and initializing a variable in a different line. So here we're declaring the price variable to be of type double in one line. Then on the next line, we're assigning a value of 12.99 to it. Click the final link, additional assignment examples. Here is just showing that we can use formulas, for instance, to assign a value to a variable. We can also take the value of one variable, such as wholesale price, and assign it to the variable price. We may also call a method, such as calculate price, and assign the return value from the method to the variable price. Sometimes we want to create a variable, initialize it, and then make sure that that value that we've initialized the variable to doesn't change. This is a constant because the value stays constant from the time it's initialized through the rest of the program. To create a variable that is a constant in Java, we use the final modifier. Once we've initialized the value of the variable, then that value cannot be changed. If we try to change it in our code, we will get a compiler error. As another naming convention rule for variables, when the variable is a constant, we put the name in all uppercase letters and use underscores to separate the words. This is to signify to other programmers that the variable is a constant and its value cannot be changed. It's important to have a basic understanding of where in memory your variables will be allocated. there are two areas of memory, stack memory and heap memory. Stack memory is short-term memory. Short-lived variables will be allocated in stack memory. Local variables, those variables declared inside of a method, are short-term variables and will be allocated in stack memory. Heap memory is long-term memory. The objects that you create in your program will be allocated in heap memory, along with the attribute variables that those objects contain. Java has many operators. Here we're going to look at the arithmetic and increment and decrement operators. In subsequent modules, we'll look at some of the other operators we have available to us. So let's begin with the arithmetic ones. Java has the traditional arithmetic operators you would expect. We have the plus operator, which allows us to do addition, the minus operator, which gives us subtraction, the asterisk, which performs multiplication, the slash, which does division, and the percent sign, which is the modulus operator. I think the first four are fairly self-explanatory, but the modulus operator may be new to some of you. So let's take a look. We have an example, 10 mod 6. What you do is you take 10 and divide it by 6, and then you keep the remainder of the division. So 10 divided by 6 gives you 1 with a remainder of 4. You throw away the 1 and you keep the 4. This is the same type of math that you probably did when you were a little grade school kid and you didn't know about decimal places. Now let's look at the increment and decrement operators. So click the increment decrement button. The plus plus symbol is the increment operator, and it adds 1 to the value of the variable. The minus minus operator is the decrement operator, and it subtracts 1 from the value of the variable. These operators are shortcut operators. For instance, I could say x equals x plus 1 to add 1 to the value of x. But the increment operator can be used as a shortcut, and I could just say x plus plus instead. Now there are two versions of each of these, the pre-increment and post-increment, and the pre-decrement and the post-decrement. And it depends on what side of the variable you put the plus plus operator or the minus minus operator. For instance, if I have plus plus I, that is the pre-increment version. And if I have I plus plus, that is the post-increment version. Same thing with the decrement operator. So it works slightly different depending on which version you use. So let's take a look at an example. Let's look at pre-increment. If I have an integer I with a value of 6, and then I want to pre-increment I and assign its value to j, what will happen is I will increment I by 1 to get 7, and then assign 7 to the variable j. So both I will have a value of 7 and j will have a value of 7. So the pre-increment version increments the value and then does the assignment. The post-increment works the opposite way. You first do the assignment and then the increment. So let's take a look at an example. If I have an integer I which equals 6, and then I have an integer j which I want to assign the value of I plus plus, what will happen is I will first take the value from I and assign it to j, and then increment the value of I by 1. So at the end of this, I will have a value of 7, and j will have a value of 6. This same thing happens with the pre-decrement and post-decrement versions. So you must be very careful about which side you put the plus plus or the minus minus operator on your variable. In the previous slide, we talked about some of the operators that we have available to us in Java. But what happens if we have more than one operation on a single line of Java code? For instance, what if we had 1 plus 2 times 3 plus 4? Should we go left to right and add the 1 plus 2 first? Or should we go right to left? Or is there some other order we should do? we're not going to go over all of the operators in this table, as we'll be seeing most of them in subsequent modules in this course. But this table shows us the precedence that the operations take over one another. So for instance, from this table, we see that multiplication has a higher precedence than addition and subtraction. So in my previous example, we would want to do the multiplication first and then the addition, and not go left to right. We'll be seeing this in the next slide. Now, I don't expect you to memorize this operator precedence, but you should know where you can find it if you have any questions. To illustrate why it's important that we understand operator precedence, and also how we can override operator precedence using parentheses, we're going to take a look at an example. Here we have an equation, c equals 25 minus 5 times 4 divided by 2 minus 10 plus 4. We'll first do it going left to right with the order of operators. Then we'll do it using the rules of operator precedence. And then lastly, we're going to override these rules with the use of parentheses. So let's see how some may think it might be done by going left to right, which is incorrect. So first, we would take 25 minus 5 and get 20, then multiply that by 4 to get 80, then divide that by 2 to get 40, then subtract 10 to get 30, and then add 4 to get a total of 34. Remember, this is incorrect. This is not how Java will do it. Java will follow the order of operator precedence. So let's click the Rules of Precedence tab to see how Java will do it. Now we've used parentheses to highlight the order in which these operations will occur. So the first thing that will happen is the multiplication, because that has higher operator precedence than the subtraction and the addition. But wait, you also have a division, which is at the same operator precedence as multiplication. Okay, when you have two operators at the same level of operator precedence, then they go left to right. So we will do the multiplication and then the division, because the multiplication is further to the left than the division operation. So let's see what would happen here. So first we'll take 5 times 4 and get 20, then divide that by 2 to get 10. Now we're left with subtraction and addition, which are at the same level operator precedence, so now we will go left to right. So 25 minus 10 will give us 15, then minus another 10 will give us 5, then add 4, and we'll get, as an answer, 9. Well, what if I don't want my equation to follow that order of operator precedence? Well, then you can override it using parentheses. So let's take a look at that. Click the Overriding Using Parentheses tab. Now, in this case, what we'd like to have happen, there are many times that we have a value in a variable of one type, and we'd like to copy that value into a variable of a different type. Now, sometimes this conversion can be done automatically for us, and sometimes it cannot. Here we have an example where the conversion cannot be done automatically by the compiler, and so we get an error message. We have an integer called num1, which has a value of 53, and we have an integer called num2, which has a value of 47. And we'd like to add those two integers together to get a result of 100, and store that result in a variable called num3 of type byte. Now, if you remember from our discussion earlier on the primitive data types, the byte data type can hold values from -128 to +127. So here we're trying to store a value of 100 into the num3 variable of type byte. So its value is okay for the byte data type, but yet there is a problem. You see, at compile time, all the compiler knows is that we're trying to store an integer, because we've added num1 and num2 together, which are integers, into a byte. Now the integers have a range from -2 billion approximately to +2 billion approximately. So at compile time, the compiler doesn't know what value is going to be calculated here. It just knows that it has a possibility of being very small or very large, much smaller or much larger than what the byte data type can hold. So the compiler is going to give us an error. It's going to give us an error of possible loss of precision because it doesn't know if this would result in an error or not at runtime. So it's warning us. So this is an instance where the compiler cannot do the conversion for us automatically and where we will have to do what's called a cast. If the compiler could do the conversion for us automatically, it is called promotion. And we'll be talking more about casting and promotion in the next slides. Sometimes the compiler is able to do the conversion for us from one data type to another. This is called promotion. This happens when we're going from a type that has a smaller range of values to a type that has a larger range of values. Here in our diagram we see the automatic conversions that the compiler can do for us. For instance, a byte can automatically be converted into a short. A short can be automatically converted into an int. A char can also be converted into an int automatically. The ints can be converted into longs, the longs into floats, and the floats into doubles. Now it isn't just that a byte can go to a short or a short to an int, but also a byte could go to an int, or a byte could go to a long, or a short could go to a float. As long as you're moving from a data type that's lower in this chart to one that's higher in this chart as indicated by the arrows, the conversion can be done automatically. We see this in the edit window on the right. We have an integer x that is set equal to 5. We can take the value of x and store it into a y variable of type long, and the conversion will be done automatically. Again, this is possible because we're going from a smaller range of values to a larger range of values. Now there is one to note that might throw some people. It's the char to an int. One might say, hey, that's a character. How can a character be converted into an integer? Well, internally, characters are just numbers. And those numbers just have a lookup into a character table that says what character to print for that number. So you can convert from characters to integers. Now, also, someone might say, well, the character data type is 2 bytes and the short data type is 2 bytes. Why can't there be an automatic conversion from characters to shorts or shorts to characters since they're the same size? That's a good question. And what you should note is that the very first bit in the bytes, shorts, ints, longs, floats, and doubles is the sign bit. It indicates the plus or the minus of that data type. The char data type does not have a sign bit, so its range of values is from 0 to approximately 65,000, whereas the short data type goes from about negative 32,000 to positive 32,000. So if you converted from a short to a char, you would lose the sign bit. So you see, even though they're 2 bytes big each, they don't have the same range of values, and so conversions between each other cannot be done automatically. Well, what do we do if we want to go from a larger data type to a smaller data type? For instance, from a long down to an int. Well, we need to use casting. So let's go ahead and revisit our example from before, where we got our possible loss of precision error. So here we have our num1 variable and our num2 variable that we would like to add together, and then we'd like to store its value in a num3 variable of type byte. Now we've already talked about why this is not possible automatically. So let's see how we can use casting to do it. With casting, we are basically going to override the compiler's warning. We're going to go ahead and tell the compiler to convert the number to our desired data type, and we're going to accept the fact that there might be an error or possible loss of precision. So we have to do this very, very carefully. So here we know that the numbers are going to add up to 100, which is an acceptable range for the bytes. So we're going to go ahead and cast that integer to a byte. The way you do it is you use parentheses, and in the parentheses you put the data type that you want the value converted to, and you put it in front of the value. So here we have to make sure that we do the addition first, the num1 plus num2. So that is why those are in parentheses. That gives us an integer, and then we are going to cast that integer into a byte by using the cast. Now this will override the compiler's warning to us, so we must accept the consequences of our actions here. So you're going to want to make sure that the value that gets calculated is acceptable for the data type that you are converting to. Otherwise, you can get some weird results. Now let's take a look at another example of casting to see what can go wrong and why you have to make sure to be very careful when you cast from one data type to another. Here we have a variable called myInt of type integer and another variable called myLong of long type. We're setting the value of the long variable to a value that is outside the range of the integers. And then in line 3, we're going to cast the value from the myLong variable into the myInt variable using casting. So we're overriding the compiler's protection, and we're telling the compiler to go ahead and do the conversion anyway. As you can see, what happens when we cast the long value to the integer value, it gets garbled and becomes a negative number. So what has happened is part of the long data gets tossed away during the conversion, and that causes the integer value to get all garbled. So you have to make absolutely positive that when you do a cast from a larger data type to a smaller data type, that the value you're casting from is appropriate to the variable that you're casting into. Let's take a look at another example where casting might be necessary. In the top left edit window, we see we have three variables a, b, and c, all of type short. We are setting a equal to 1 and b equal to 2. And then we are going to set c equal to a plus b. This will result in a compiler error of possible loss of precision. Now why is that? The reason is that when Java does math, the lowest type of math that it can do is integer math. So even though it's adding two shorts together, it will convert those to integers and then add them together to get an integer result. And as we saw from before, you can't take an integer and try to put it into a short variable unless you cast it. What you need to note with Java and addition is that if you add 2 bytes together or 2 shorts together or a byte and a short, you will always get an integer result. If you add 2 integers together, you will get an integer result. Now if you add an integer and a long or 2 longs together, you will get a long result. If at least one of the operands in your addition is a float value, you will get a float result. And if at least one of the operands in your addition is a double, then you will get a double as a result. So the smallest result you'll get with addition is an integer, but you may get a long, a float, or a double depending on what's being added together. So you have to be careful of that when you're trying to add two things together and then store it into a variable. You have to realize what will the result be that I'm going to get. So what can we do in this scenario? Well, we have two options. One we can see in the upper right hand edit window. Here we declare the c variable as type integer. This will solve our problem because now when we add a plus b and we get an integer together, we're storing the result in an integer. And that's perfectly fine. Our other option is what is seen down in the edit window in the bottom of the screen. Here we add a plus b together to get an integer, and then we cast the result to a short value and stick the short value in the c variable. Now you have to remember that if you do this, you have to make sure that the result of the a plus b addition is within the valid range for shorts. Now click the Assignment tab, and let's take a look at another area where we might run into some trouble. In the previous example, I mentioned that during an addition operation, the lowest result you could get was an integer result. And that if you had a long or a float or a double as one of the operands, you would get a long or a float or a double, depending on what the highest operand was. That happens not only with addition, but with also subtraction, multiplication, division, any of the mathematical operations. Now it isn't just enough that you are aware of the final result of your equation, you must also be aware of any intermediate results and what is the possible range of intermediate values as your result gets calculated. This can lead to some tricky problems. So here we're going to illustrate this in an example. Here we have two calculations. One that calculates the number of days old that a person is, and another one that calculates the number of seconds old that a person is. The first one takes the number of years a person is times 365 and calculates an integer to get the number of days. The second one takes the number of years old a person is times 365 times 24 as a long value times 60 times 60. Now the 24 long value is important. By inserting this 24L in this equation instead of just 24, we are causing the intermediate result of this equation to be a long result. If 24 did not have the L on it, it would be an integer, and the intermediate result that is calculated would be an integer. And it's possible that the number of seconds old that a person is, depending on their age, could be greater than 2 billion, which would put it outside the range of integers, and we would get a garbled answer. It isn't just enough that we are taking the result and assigning it to a long value. You must make sure that the intermediate calculation is also a long to make sure there is enough room to hold any intermediate values. So in this case, with an age of 32, we get that the person would be 11,680 days old and approximately 1 billion seconds old. Now let's look at example 2. Now in this example, we've increased the age to 70 years and taken off the L on the 24, thus causing the intermediate result to be an integer result. And then we're going to assign the integer result to a long variable, which is the number of seconds. But it doesn't matter that we're taking the integer result and assigning it to a long. The damage has already been done before the assignment. You see, the number of seconds calculated will be greater than 2 billion, and we will garble our answer. As you can see in the output window, we get output of around negative 2 billion, which is obviously wrong. In this module, we've talked about variables. We've learned how to declare them, initialize them, and use them. We've also learned about the 8 Java programming language primitive data types. These were byte, short, int, long, float, double, char, and boolean. We've also learned about constants and some of the operators we have access to, such as addition, subtraction, and the increment and decrement operators, as well as promotion and typecasting from one data type to another. In this module, we're going to focus on the details of creating and using objects and how their storage in memory differs from that of primitives. In the previous module, we discussed the primitive data types and how to use them with variables. In this module, we'll be focusing on objects and object reference variables. We'll learn how object reference variables are stored in relation to primitives. In the previous module, we discussed the primitive data types and how to use them with variables. In this module, we'll be focusing on objects and object reference variables. We'll learn how object reference variables are stored in relation to primitive variables in memory. We'll also take a look at the string class, as well as take a look at the class library specification to learn about other classes that you have access to. In the previous module, we were dealing with primitive data types. And when you declared a variable of a primitive data type, you stored the primitive in the variable itself. But Java is an object-oriented language, so we really want to be dealing with objects. Now, with dealing with objects, you also need a variable associated with it. But it works different than with the primitives. You don't store an object inside of a variable like you do with the primitives. What you do is you store a reference to the object inside the variable. Now, a reference is like an address to a house. In the previous module, we were dealing with primitive data types. And when you declared a variable of a primitive data type, you stored the primitive in the variable itself. But Java is an object-oriented language, so we really want to be dealing with objects. Now, with dealing with objects, you also need a variable associated with it. But it works different than with the primitives. You don't store an object inside of a variable like you do with the primitives. What you do is you store a reference to the object inside the variable. Now, a reference is like an address to a house. It allows you to find that object. So using that reference, we can call up that object and ask it to do something. We can either access its attributes or we can access its methods. So just like we can send a letter to a house because we have its address, we can access an object using its reference or its address. Here we have the shirt test class that we used in a previous module to create a shirt object and then access it. In the following slides, we're going to be taking a much more detailed look at the creation of the myShirt object reference variable and the creation of the shirt object, and how these two are tied together, and how the object reference variable is used to access the shirt object. The first thing that you need to make sure that you have when you are creating an object is a place to store the reference to the object. So as you can see in line 6 of our shirt test class in the main method, we are creating a variable called myShirt of type shirt. Now, this does not create a shirt object. What it does is it creates a reference variable that can hold at most one reference at a time to a shirt object. You see, you never have the shirt object. You only ever have a reference to a shirt object. And using that reference, we can then access an object's attributes or call its methods. Remember, a reference is like an address to a house. It allows us to find that object in memory and access it. So as you can see, what's happening in memory when this line of code executes is we get a myShirt variable allocated in stack memory, which again can hold at most one reference to one shirt object at a time. So once we have our object reference variable created that can hold a reference to our object, we can then create the object using the new operator. We are issuing the command new shirt. This will create the shirt object. Now, objects are allocated in heap memory, as we can see in our memory diagram. And the attributes for that object are allocated also in heap memory, along with the object itself. Now, the new operator has a return value. Its return value is the reference to the object that it has just created. And so we need to assign that return value to our variable, myShirt. So now in this slide, we can see that the object's reference variable is being returned from the new operator and that it is stored in the myShirt variable. This then creates a sort of link between the myShirt variable and the shirt object itself. And then again, using this reference, we can access the object's attributes like shirt ID, description, color code, or access its methods, such as display shirt information. Now in this next line of code, we are using the reference stored in the myShirt variable along with the dot notation to access the color code attribute of that object. And you can see we are changing the color code from a U, which stands for unknown, to a G, which stands for green. Now once again, once you have a reference to an object stored in your reference variable, you can then use the dot notation to access its attributes and either read them or write to them, or to invoke the object's methods. So let's take a look at a much more in-depth example to make sure that we have the difference between what an object is and what an object reference variable is, and how these two correlate to one another. So in line 4, we are creating our myShirt variable, which we had in the previous example, and the shirt object from the previous example. Notice how the reference address is stored in the myShirt variable, which creates a link to that shirt object. Then in line 5, we are creating a different shirt variable called yourShirt and a different shirt object. And we are tying those two together by storing the reference to that shirt object in the yourShirt variable. So we have a myShirt variable pointing to one shirt object and a yourShirt variable pointing to a different object. Then we are using the myShirt reference variable to call the displayShirtInformation method on the first shirt object. Again, notice the use of the dot notation. Then we are also calling the displayShirtInformation method on the yourShirt object. And then, once we have finished executing the displayShirtInformation method for the myShirt object and for the yourShirt object, we are going to change the value of the color code for both of these objects. So we are going to change the myShirt color code to be an R, which stands for red, and the yourShirt color code to be a G, which stands for green. So notice once again the use of the object reference variable and the dot notation. And then lastly, we recall the displayShirtInformation method for both of those objects to show that the myShirt object now has an R for its color code and the yourShirt object has a G for its color code. As I mentioned previously, an object reference variable can store up to, at most, one reference to an object at a time. It may not store a reference at all, but it can store up to one at most. Now, even though an object reference variable can only refer to one object at a time, this does not mean that an object cannot have more than one reference variable referring to it at the same time. It is also the case that an object reference variable does not have to store the same reference to the same object throughout its lifetime. It can refer to one object at one point and then another object at another point by changing its object reference value. So let's take a look at both of these scenarios. That is, an object that has more than one reference variable pointing to it, and the changing of a reference variable from referring to one object to another object. So in this example, we are again creating a myShirt variable that will hold one reference to a shirt object and creating that associated shirt object. We are also creating a yourShirt object reference variable and its associated shirt object. Now in line 6 is where things get interesting. We are taking the object reference stored in the yourShirt variable and copying it into the myShirt variable. So now the myShirt reference variable is no longer referring to its original shirt object, but it is now referring to the same object as the yourShirt variable. So we've seen that a reference variable can change its value and point from one object to a different object. And now we also have the situation where we have two reference variables referring to the same object. So let's see what happens in this situation. Let's use the myShirt object reference variable to change the object's color code to an R. So doing this will change the color code referred to the myShirt object to an R, but it also changes the color code of the object referred to by your shirt. So now if we use the your shirt object reference variable to change the color code of the object associated with it to a G, we are basically overwriting the R that we just stored in that color code attribute, since both your shirt and my shirt refer to the same object. So it doesn't matter now which object reference variable you use, you will be updating the same object. So, to reiterate, an object reference variable can store up to, at most, one reference to an object at a time. An object, however, may have more than one object reference variable referring to it at one time. And also, an object reference variable can change its reference value. It can refer to one object at one time and then a different object at another time. Now let's take a look at the string class for a second. The string class is sometimes confused with a primitive. But remember, our primitives are byte, short, int, long, float, double, char, and boolean. But the string class is confused sometimes with a primitive because of the way it operates. For instance, you do not have to use the new operator to create a new string object. Now, with most all other objects, you do have to use the new operator. But this is an exception because we use strings so often. So notice in our upper edit window, we are just putting the string Fred Smith in quotes. Java will then create the string object associated with this without having to use the new operator. As we see in the lower edit window, you can use the new operator to create a new string. But this is redundant and not necessary. So let's see how string objects are kept in memory. Now, since a string object is an object and not a primitive, we have the same situation we had before. We will have an object reference variable that holds the reference to the object. So in this case, our object reference variable is called myName. It holds a reference to the string object, which is allocated in heap memory. And then we are also showing that the actual characters of Fred Smith are kept in another portion of heap memory, which has a reference to it from the string object itself. So you see, a string object is like any other object. In fact, when you set one string object equal to another string object, you are really just passing object references around from one reference variable to another, just like we saw in the previous slide. Another reason that some people think that the string object is a primitive, besides the fact that you don't have to use the new operator, is that it acts like a primitive with the use of the plus symbol. Now, with most of the other primitives, when we use the plus symbol, we are doing addition. So if we say 3 plus 4, we'll get 7. But when you use it with strings, you are doing string concatenation. So in this example, we have a string attribute called name, which is equal to Jonathan, and a string attribute called job, which is equal to ice cream taster. And then in the display method for the object, we are printing out the string my name is, and then concatenating the name variable plus I am a, and concatenating the job variable. So in this case, we are doing string concatenation. So we will get my name is Jonathan, I am a ice cream taster. So the fact that you don't have to use the new operator to create a string object, and you can use the plus operator to do string concatenation, leads some people to believe that it's a primitive because it has these primitive-like qualities to it. But it is an object, and you are creating object reference variables when you create string variables. So just make sure that you keep that in mind. During this course, and after this course, as you explore Java, you're going to encounter many classes. And you're going to need to find information about those classes, such as what attributes they have, what methods they have, what the constructors are for those classes. And so you're going to need to turn to the Java API documentation. Now you can either access it online, or you can download it from the java.sun.com website. If you wish to access it online and take a look around, you can do so by going to java.sun.com/j2se/1.5.0 class/docs/API/index.html. Now as you look around the API documentation, you're going to see that the window is broken up into 3 frames. In the upper left-hand frame are your packages. Now we haven't talked about packages yet, but basically you can think of them as logical groupings of classes to help organize things. So if you click one of the packages in the upper left-hand frame, it will list the classes in those packages in the lower left-hand frame. And then if you click one of the classes in the lower left-hand frame, the class will be displayed in the right-hand frame. Now this will tell you information such as what package the class belongs to, what class or classes the class inherits from, what interfaces the class implements, some information about the class and how to use the class, what the constructors are for the class, what the attributes are, and what the methods are. So a wealth of information. Now it takes a little bit to get comfortable with using this help. So why don't you go out there, take a look around, because you're going to need to be able to use this, because it's very difficult to try to remember all of the methods and all the attributes of all the classes. In this module, we learned how to declare, instantiate, and initialize object reference variables and how they differ from primitive type variables. We also learned how objects and object reference variables are stored in memory and how they relate to each other and how they differ from primitive variables. We also learned about the string class as well as how to find out about other classes in the J2SE class library specification.